Let's go back to our example of downsampling filter, which should attenuate frequencies starting at 11 kHz at a sampling rate of 44.1 kHz. We would like to have minus 60 dB attenuation in the stop band. Hence, we obtain the normalized frequency for the start of our stop band as 11 divided by 44.1 times 2 times pi, and we have 0.5 pi. This is the start of our stop band. Hence, our desired frequency response is 1 between frequency 0 and omega s, or better, between minus omega s to plus omega s, to also include the negative frequency axis. Now, we take the inverse DTFT of the ideal desired frequency response, h desired, of omega, to obtain the ideal impulse response, h desired of n. Since at first we assume an ideal filter, we set the end of the passband identical to the beginning of the stop band. So hc is equal to hs. And this is the end of the passband identical to the beginning of stop band. So here we have our h of t, our desired. So this is the ideal. And we have this integral. This is the h of t. And when we solve, we have this. We must remember this trigonometric property here, that the sine of omega, it's equivalent of this sum of exponentials. So it's a 1 divided by 2 times j, the imaginary number, times e to the power of j omega minus e to the power of minus j omega. And if we replace this here, we have this. So the h desired of n equals to the sine omega c times n divided by pi times n. So let's take a look at the approximation of an ideal low-pass filter using a rectangular window and delay. We've seen that the impulse response of an ideal low-pass filter is given by this equation here. So it's the sine of omega c times n divided by pi times omega n. Truncating the impulse response, so multiplying by a rectangular window, so it has a length L, and applying a delay of nt equals to L minus 1 divided by 2. So we're replacing here, so n, and we will apply a delay, and we will make this delay equals to L minus 1 divided by 2. We can also use SimPy to solve this. So here I'm importing SimPy, and I'm importing sine, symbols, simplify, pi, lambdify, and limit. Here I'm defining my symbol of omega c, and other symbols are the n and the L, so the length and the n. Here then I am defining the delay, so it's L minus 1 divided by 2. And here we have our sine of omega times n minus nd, so it's the delay, divided by pi times n minus nd, and nd is equal to L minus 1 divided by 2. So when we set SimPy, it gives us this expression here, which is equivalent to this one here. We can also see that the limit, when n is equal to L minus 1 divided by 2, we would have here a division by 0, and we can take a limit to see that's the value. So the value is omega c divided by pi, the limit when n is goes to L minus 1 divided by 2. So here we have the plots. So we will assume that L is equal to 16, and I'm here using lambdify, so I want that these symbolic expressions becomes available to use with NumPy, so I can use this lambdify instead of redefining them using NumPy. Then I'm defining some axes and figures for our plots. I'm using interact again, so we can use the slider to change the values of the length of our filter, and also the omega c. But for now I will leave like this. So here we are using again frac z to calculate the frequency response. Here we have the impulse response, so we're just doing something for even and for odd values of L. So depending if L is even, we will use the impulse response like this, and if it's odd, we will have this impulse response given by this here. So we have this value for when I is equal to the delay. So we can see here there's this big difference, because for even there is here supposedly at 7.5 when we're using a 16, but if we go for example to 15, and then we need this value here, and when n is equal to the delay, we would end up with that what we discussed before. This would go to 0, so we need to take the limit and we need to find out the value for n is equal to L minus 1 divided by 2, and this is what we are doing here. Then we are having the magnitude in dB, also some annotations to find out the omega at minus 3 dB and the omega for the peak of the side lobe, and also we are plotting phase, and that's what we have here now. If we use our example that L is equal to 16, so 16 minus 1 is 15, divided by 2 is 7.5, and we can have here calculate our delay, and it's equal to 7.5. So this is what we're doing. L is equals to 16. Our delay to make the resulting filter causal is 7.5. Then our filter becomes this expression here, and this is our resulting causal FIR filter with a rectangular function. So we can see that the pass band has some ripples. So we can zoom in a bit to see the ripples. So we see the ripples in the pass band, and they are more or less plus or minus 0.5 dB, corresponding to a factor of 6% of over or undershoot, and that's usually okay. But we can also see that this filter has maybe minus 10 dB attenuation, and the first side lobe has only about minus 20 dB attenuation. So if we go back to, we have here the second side lobe here is more or less minus 20 dB attenuation, and is not satisfying our requirement for at least minus 60 dB starting at normalized frequency 0.5 pi. For the phase plot, we have a delay of 7.5, and this is a linear phase, so we expect the phase to be minus 7.5 times omega. And we can verify this in our plots. For example, if you take a certain frequency and then you obtain 7.5 times if it's 0.1, and then pi 180 divided by pi is more or less 135, and we can see here we are not in degrees, but you can also set and look, for example, here when there is a value for omega and you see the angle, and you just make these calculations and you see that this is how we verify the delay. Now we have a filter with the minimum squared error in comparison with the ideal filter, but this is not really what we like to have. The problem is that we get the so-called Gibbs phenomenon. It says that the error appears as ripples along the magnitude of the passband and the stopband. The interesting part is that the ripples near the passband and stopband, they don't become smaller as L becomes larger. But they only become more narrow. This is the result of convolving our ideal frequency response with the sinc function from the rectangular window. The sinc function only becomes narrower as we increase its length, but the height of the ripples, they stay the same. And we can verify. If we increase, we see it's becoming narrower, but we don't see significant change in the height of the This means that the maximum error that we obtain does not become smaller as we increase L. So observe that the ripple size near the passband and stopband only becomes more narrow, hence a reduced area and hence a reduced quadratic error, but their height does not become smaller with increasing L. Here they always stay at around 0.1 in the stopband, which corresponds to about minus 20 dB, which is not sufficient for our aliasing filter example. To see how the Gibbs phenomenon results, we can take a look at our scheme in the frequency domain. So in principle, we multiplied our ideal impulse response with the rectangular window. In the frequency domain, this means a convolution of the ideal frequency response with a phase change through a delay NDE with the frequency response of the rectangular window. The latter is a narrow sinc function which corresponds in ripples to the sides of its main lobe. And those ripples are what shows up as Gibbs phenomenon. If we make our window longer, the sinc function becomes more narrow, but the height of the ripples does not decrease but stays constant. Actually, in most applications, what we want is not minimizing the quadratic error, but minimizing the maximum error. So basically, we chose the wrong error measure. This suggests a modification to lower the height of the ripples. And instead of a rectangular window, we can take alternative windows which have lower ripples in the frequency domain. And very common used windows are the raised cosine or the sine window.